The next energy I want to talk about, the next form of energy, is elastic potential energy. And keep in mind, gravitational potential energy was energy due to a location. The object existed in a certain place within the gravitational field of another object. And with elastic potential energy, this is energy an object has due to its deformation, due to its new shape. And we can think of it as the work required to stretch or compress an object. And I want to discuss Hooke's law before we move on. Hooke's law states that a restoring force on a spring, so the force that's going to bring it back to its rest length, is proportional to the stiffness of the spring. So this is the stiffness constant, or the spring constant. The only way to change that is to switch out the spring. Even if you overstretch the spring, the stiffness constant remains the same. It's just you've changed the plasticity, which is something else. So it's proportional to the force is proportional to the stiffness and proportional to the amount of stretch or compression. So what I mean here is, imagine if I have a spring attached to a wall, and that's the normal length of the spring. If we compress the spring, that distance is our x. Or if we stretch the spring, that distance is our x. And so what Hooke's law is saying is, for a spring that follows the law, the further the spring is stretched, or the closer the spring is compressed, the harder we have to push or pull. So when we're talking about the work required to stretch or compress a spring, that would be we're fighting against the restoring force for some sort of distance. Well, keep in mind here, we can consider work to be the area under a force, but displacement graph. And according to Hooke's law, if a spring follows that law, the line or the relationship should be linear. So that tells us the work here would be the area under this triangle. So if this is the maximum force we're applying, the area of the rectangle would be this. But that's not the work we're putting in. We haven't been applying that force the entire time. That force has been growing. So if we want an area that represented the actual work, we would take the average force we've been applying. Because this area here would equal that area there. So the average force, in order for that to occur, the average force would have to be half of the maximum force. So we get the elastic energy, which is represented with a capital U subscript S, is 1/2 K times X times X. or, as you see it in your formula chart, 1/2 kx squared. So that's your potential energies. And that's all I got for you.